This is our final project for CS 5590. Your cache is my cache about side channel attacks. This is by Aiden, Claire, and Jeremy. Quick overview. We're going to do an intro, background, motivation, then jump into the methodology and results and the conclusion. So what is a side channel attack? First, we kind of need to understand a CPU cache, which all CPU cache is stores frequently accessed data. Uh, Usually the L3 is shared between all cores and sometimes the L2. And because this L3 is shared, this can be exploited through a side channel attack. So an analogy, just to kind of explain it clearly, let's say you have a library, and at the library you have a quick checkout table. So when people come check out books, when they return them, it'll go on the quick checkout table. This means, someone else is likely to grab it, and they don't have to go all the way to the back shelves to find it. In this scenario, we have two victims at the quick checkout table, and we have an attacker looking at them. So let's say you want to see what someone else is studying for without seeing what they're actually reading. So in this scenario, the attacker in this picture would actually be outside the library. So what you could do is you could wait outside the library and time someone how long it takes them to get their books. Then when they leave, you could clear off some or all of the books at the quick checkout table, and then wait for them to come back and time them again. Now, if they took longer to grab the books, they probably read the books you removed from the quick checkout table, because that means they had to go to the back of the library and find the book. So in this scenario, the library would be the RAM or the memory, and the quick checkout table would be the cache. And you can see those are two processes. So some key points that we're indirectly exploiting information. We're not looking at the code, right? We're outside the library looking in. But some attacks can still be monitored and detected by the victim. Some can't. So the flush plus flush that was found in about 2016 or 2017 and published in a paper, and it is completely stealthy and undetectable at the time it was published. So what could you actually gain from this? What's the impact? What would you want to monitor? It's been shown you can get cryptographic keys. You can kind of reverse engineer. You get keys, you can get keystrokes, you can get website or app fingerprinting, seeing which website someone's visiting. You can see which function calls are being used by a different process, or you can just infer computations, see if another process is doing machine learning or crypto mining, video editing, whatever it may be.
Now let's go into some background for the specifics about the cache attacks that we used in our project. So we focused on four major cache attacks, and these are flush and reload, prime and probe, flush and flush, and evict and reload. So all of these cache attacks exploit the shared cache. So for flush and reload, the main requirement here is that a component of the x86 cache is shared and is available to be accessed by both the attacker and the victim. Another requirement is that it has this flush function. And again, in x86, it has CL flush, which works perfectly. So in short, the attacker flushes the cache using CL flush and then waits for the value to be reloaded and times the access for the reload. So the CL flush instruction, which from the x86 documentation, invalidates the cache line that contains the linear address specified with the source operand from all levels of the processor cache hierarchy. So let's consider a cache here, where the red block represents the address that's being targeted. The attacker will go in and flush this address and then wait a certain amount of cycles. After this waiting, there are two possible outcomes. First, the attacker does not use the cache location and the status of the flushed cache persists. Second, the victim does use this address in its instructions and it will go into memory to retrieve the data and put it back into the cache. After the attacker waits their specified amount of cycles, they will then reload this address and begin timing. A slow retrieval means that the shared memory needed to be accessed, implying the victim did not use the address. And a fast retrieval means the data is back in the cache and the victim did use this address. So next is prime and probe, and its distinguishing factors are that it does not require a shared memory, and it targets the last level cache. As the name suggests, this attack has two phases. The priming phase, where the cache is filled with values by the attacker, and the probing phase, where it checks again these locations and the time to access and to see if there is a difference. So let's again consider our cache, but with no shared memory. First, the attacker fills or primes the cache sets with their own data. This is done by accessing multiple addresses that map to the same cache set, but maybe in different lines. Then the victim program runs, accessing different locations in the cache, which will then have to go into their memory and retrieve them. Then in the probing phase, the attacker goes in and tries to access these cache lines. If the accessing is fast, then the victim did not use the cache location because it is the same value that was there when the attacker primed it. However, if it's slow, that means the victim did use this location and loaded their value in. Next is Flush and Flush. Flush and Flush relies only on the execution time of accessing the data in a cache. In a similar way to Prime and Probe, there is no shared memory required, and it can be run very fast and stealthily because it only requires the cache flushes. And once again here, it is using CL Flush because we're in the x86 architecture. So the main idea is that this CL Flush runs in an endless loop of flushing it and timing it. So if we were focusing on a specific address here in our shared cache, the attacker flushes the address and then waits a certain amount of cycles again before performing another flush. CL flush here can be used because it exits early if there's nothing in the cache location, making the timing results an indicator of the cache use. So from this, the attacker can determine if CL flush occurred fast, if the data was not used by the victim and therefore not in the cache, or if it was slow and then the data was in the cache and it had been reloaded by the victim. So the final cache attack we looked into was evict and reload. This attack is almost identical to flush and reload, except there's no flushing, and instead the attacker overwrites the cache set that contains the targeted memory address and fills it with other addresses, essentially acting as evicting the data. In our cache demonstration here, the attacker is focusing on a specific location. The attacker then fills the cache set or the eviction set with their data. Then they wait a certain amount of cycles where the same two options as before could happen. First, there could be no access and the cache will not be changed. Or the victim could access the data and it would be reloaded from memory. In the same way, it's slow, then the attacker needed to go in and reload it from memory, meaning it was not used by the victim. And if it was fast, that means the victim did access it and it was back in the cache. So these different side channel attacks are all very dangerous, and that's why being able to detect them apart from regular cache use is super important. So now on to the motivation for our project. Some of these side channel attacks require a shared memory, but they all use the shared cache. So this can be found in the shared on-chip buffers. So this is the actual physical memory that is shared between the components and the cores of the system. So as we can see here in this Intel Core i7-4790K chip, the last level cache is shared between all the cores. And here it is. So this can lead to multiple security issues. So since all the data in the different caches is consistent, and that is here with this cache consistency where all copies of the data in all levels of the cache is the same, it can be vulnerable because some of these components and cores can have different privileges that all access the same data. And as we discussed earlier, the cores can monitor the behavior of these shared caches. And as we said, that's exactly what these side channel attacks are doing. So, what part of this is still relevant to today? So, despite these cache side channel attacks being discovered in the mid 2010s, these attacks are still relevant and have been changing. In the more modern computing world, cloud services require many shared resources, which could all be exploited in a similar manner. And the data can be stolen from virtual machines, which have a bunch of shared resources, and also new shared libraries just offer an increased attack surface, creating for really this ever evolving attack. So, being able to detect these types of attacks continues to be an area in computer security of great importance. So, moreover, the cache performance data is also easily available to be accessed on modern computers. So these performance counters can be collected in real time, which can provide insights into how the cache is physically being used. So we explored how we can analyze this and take advantage of these readily available performance metrics. So we have these performance counters, but how can we really use them? And as we can see here, some examples of the performance counters is cache misses, cycles, instructions, and many more that we'll discuss later on. So, in order to combine these cache attacks with a more modern solution, our project dived into analyzing these performance counters with machine learning for classification and detection to hopefully increase the security against these attacks and the defense against them.
Now on to the methodology section. So a brief overview. The overall goal of our project is to detect several types of cache-based side channel attacks using machine learning. And specifically, we're targeting flush reload, prime probe, flush flush, and evict reload, each of which exploits different behaviors of the CPU cache. And our strategy goes as follows. First, we generate real attack traffic by executing actual implementations of these attacks. And second, we collect the performance counter data using the perf tool. And then third, we use this data to train a machine learning model that can distinguish between malicious and benign behavior. And a key point is that we're doing system-wide monitoring. We're not monitoring an attacker or a victim process directly. Instead, we look at the system as a whole, and this makes our approach more general and realistic. So for our attack implementations, we implemented 4 different side-based channel attacks. The first 3, flush flush, flush reload, and prime probe, are taken directly from the paper Flush, a fast, stealthy cache attack by Daniel Gruss, and we use the original code provided by the authors to run these attacks reliably and in a reproducible way. In addition to those, we implemented a 4th attack, the evict reload. This one follows a similar principle to flush reload. Instead of using the CL flush instruction, instead it relies on eviction sets to remove cache lines before reaccessing them. And our implementation is relatively simple but effective, and it helps to round out our data set. So here's an overview of our system we use for all experiments. Our machine is equipped with an Intel i7 10th gen processor, which has 6 physical cores and 12 threads, and this is a common GPU found in laptops. And the system has 16 gigabytes of RAM, and we used updated Ubuntu version as the operating system with Linux kernel version 6.11.0, 21 generic. And for monitoring, you use the perfstat-a command, which collects hardware performance counter data across the entire system. Now, here's a real sample we collected using perf, and I'll explain each counter that we use. So for cache references, this is the total number of cache accesses. Cache misses, the number of times the data was not found in the cache and had to go to the main memory. Cycles is the total number of CPU clock cycles. Instructions is a total number of instructions executed by the CPU. Branches, total number of branch instructions executed. Branch misses, number of times the CPU mispredicted a branch. L1 decache loads, number of read operations from the level 1 cache. L1 decache load misses is the number of times loads miss the L1 cache and fetched from lower levels of or even main memory. The LLC loads is the loads that the last load accesses to the last level cache. The LLC load misses is loads that miss the LLC and had to go to main memory. The DTLB loads are memory loads that require translation via the translation lookaside buffer. And the DTLB load misses is TLB misses that need to do a full page table lookup. And then we're going to our load conditions. Now we have 3 load conditions, and we use stress-ng, which is a system stress testing utility tool designed to load and exercise various physical and virtual system components, and the key features that it can stress CPU, memory, I/O, cache, file system, network, and even more. And the table shows the loads we use. So first we have no load, which is just an idle system. Then we have an average load, which spawns 2 CPU stress workers, each running CPU-intensive operations. And then the full load has 4 CPU stressors and 2 virtual memory allocators using about a gig total. And these simulate realistic background activity that can influence performance, counter readings, and help our classifier generalize better. So now for our attack simulation, we implemented the 4 cache level attacks, and each attack is targeted to a shared library at a known function offset, and this made the attacks both realistic and reproducible. So first we have a cryptographic function from the OpenSSL crypto library, and then we have data processing from the OpenSSL TLS library, and then we have a library that handles authentication, a library that deals with data compression, and then the X11 display library, which handles GUI session activity. And these scenarios helped build a diverse data set reflecting a range of attacker behaviors and system conditions. So for benign simulation, we selected processes that naturally interact with the same shared libraries as attacks. This includes programs like OpenSSL, gzip, and some of the core Unix utilities. And we ran multiple benign processes concurrently to simulate realistic multitasking and user behavior and background noise. And this gives us a realistic control group for training and evaluation, helping us to ensure that the model doesn't mistake legitimate activity for malicious behavior. So for our data collection, step 1 is we start with a system-wide monitoring using perf stat-a. Next, we run either attack or benign processes for exactly 5 seconds. After that, we include a short 2-second period to ensure that there's no carryover or overlap between runs, and then the collected performance counter values are then stored in rows as CSV. And we repeat this process across the type of attack, the target shared library or function, and the current system condition load. And this thorough, repeatable setup ensures that our data set is balanced, diverse, and representative of real-world conditions. So for our data set, each sample in the data set is made up of 12 performance counters, all collected at the system level, and we label each sample either attack, which is 1, or benign, which is 0, and a key aspect of our data set is that it's stratified and balanced. That means that every unique combination of attack, target library, and system load collected, and we have an equal number of samples. And for each of those attack scenarios, we collected an equal number of benign samples under the same conditions, and this balance is critical to avoid bias in the training process and ensure that the model learns meaningful distinctions rather than just overfitting to imbalanced data. So some of our data set statistics, we have a total of 7,200 training samples, and out of those 3,600 benign samples, and the remaining 3,600 are evenly split across the 4 attack types with 900 samples each. And then we can see for loads, those 900 samples then split 300 samples per load, and this 50-50 split between benign and attack ensures that the model isn't biased to one class or the other, and equal distribution among the 4 attack types allows us to evaluate the model and to generalize different attack techniques rather than just overfitting to one specific pattern. And our test set is about 2,304 samples with the same splits and ratios as the training set, and this gives us roughly a 75-25 train test split. Now, the model that we used for classification is an XGBoost, which is a highly optimized gradient boosting framework built on decision trees. XGBoost is actually well suited for our problem because it works efficiently with tabular data, especially when features may be noisy or overlapping, as is in the case of performance counters. And our goal was binary classification, either attack or benign. And one major advantage of XGBoost is the ability to handle nonlinear patterns and feature interactions, which is crucial when distinguishing between subtle hardware behavior caused by different attack techniques and legitimate processes. And it's also fast. It supports GPU acceleration and produces feature importance scores, which helps us understand which events mattered most. Now on to the results section. Let's walk through the overall performance of our detection model. We see a strong performance across all metrics when it comes to precision, recall. So we see an F1 score of 0.9238, resulting in an overall accuracy of 0.2940, and this shows the model effectively balances false positives and false negatives. Breaking it down by class, the benign class has an F1 score of 9.9282, while the attack class is slightly lower at 0.9193, and this gap suggests that the model is more confident when recognizing benign behavior, which kind of aligns with the goal of minimizing disruptions to normal processes. This chart here ranks the features by their average gain. Gain is a measure of how much each feature contributed to improving splits in the XGBoost trees. So the top contributors we can see are cache misses and L1 Dcache loads. These are both key indicators of cache pressure and activity. Cache references and branch misses also rank high, reflecting execution volatility introduced by side channel attacks. Features like instructions, DTLB loads, LOC load misses show moderate importance, while the deeper features like L1 Dcache load misses and LOC loads carry lower weight overall. These rankings confirm that cache-related events are the primary detection signals, and the model learns to isolate even these among noisier counters. Now let's analyze our model under different system load conditions. Under no load, we have an accuracy of about 92.6%, and attacks are relatively cleanly distinguishable from idle system behavior. Under average load, performance actually increases to 92.97%, possibly because moderate load introduces enough contrast for the model to highlight abnormal patterns. For full load, performance dips to 87.89 probably due to system noise, and benign cache activity overlaps with these attack signals. Importantly though, even at full saturation, our model maintains nearly 88% accuracy, showing strong real-world viability in noisy environments. Feature importance shifts significantly by load level. In no load, cache misses dominate. With minimal noise, attack signals are easily isolated. Cycles and L1 Dcache loads also matter here. In average load, the model leans on DTLB loads, L1 Dcache loads, and instructions, suggesting it compensates for moderate noise by focusing on memory translation and code execution signals. On full load, cycles, instructions, and L1 Dcache loads are prominent. These reflect system-wide strain, and the model uses them for abnormal execution despite background pressure. And this adaptive shift shows that the model just doesn't memorize patterns. It reweighs relevant hardware signals dynamically depending on noisy conditions. Now, let's evaluate the model's ability to distinguish each attack type from benign behavior. And the results are that they're all basically the same accuracy, plus or minus 1%. However, in Flush Flush, which is known to be a stealthy attack, and the paper that introduced it claimed it to be stealthy, it's especially for performance counters, it still shows high accuracy. It's slightly lower than others, though. And these results show that our detection model generalizes well across attack strategies, even for some of the evasive ones. And each attack leaves behind a distinct performance counter fingerprint. For flush reload, LLC load misses and cache misses are the top features, and this is consistent with repeated probing of shared memory addresses. For prime probe, it relies heavily on L1 Dcache loads and cache misses, as this attack floods and monitors cache sets. Cycles, instructions, and branches show up due to execution variation introduced by set probing. And these patterns reinforce the idea that attacks create unique pressure on specific cache levels and memory components, which our model learns to recognize. Continuing with the remaining attacks, Flush Flush, surprisingly high cache misses and L1 Dcache loads, though this attack kind of avoids reloads. And this may be due to indirect noise from the attacker's loop, as it runs on an infinite while loop, and memory flushing. Evict reload, we have high cache misses LLC loads and cycles. This attack manipulates and then monitors memory, um, producing consistent eviction footprints. Branch misses and DTLB load misses also contribute, pointing to heavy memory access footprints of the reload phase. In both cases, we see that even attacks designed to be stealthy, such as Flush Rush, still disturb the hardware in detectable ways. And though the feature signatures differ significantly. Now on to a little demo of our detection model.
So I'm going to do a quick demo. And in this demo, we'll run our demo file. And this file is a script that will load a saved model that we've already trained. And what it'll do is it runs perf on 5-second intervals, and then takes that perf data and then classifies it. And it'll tell us whether the current system monitors are showing benign activity or attack activity. So we'll run the demo first and get a couple benigns, and then what we'll do is we'll run a flush reload attack here, targeting the standard C library, specifically at the offset where printf exists. So we're going to run, and then we'll get a couple benigns here. So now it's starting the monitoring. There's one. There's another. Then after 3, I think we can start running this. It'll probably be after the 4th. Oh, there we go. It's already detected the attack. And we can see that our model correctly can detect attacks live, meaning it's efficient enough, can do it quickly, and it can warn users if they're being spied on.
Let's take a look at some of the takeaways from our work. Some of the limitations. It is a controlled environment, which can be beneficial to isolate and have a sandbox, but it's not that realistic. Real world systems are a lot messier and have different things going on in the background. The benign processes might not be that diverse. We didn't have common things like browsing, which could be a big one. And the features were fixed. They didn't have any timeline info, which might miss slower or stealthier attacks. And it's sensitive to system noise. Background noise and context switches could skew the results, and we weren't able to test obviously every possibility there. So we got 92% accuracy, which we're very happy with, and it works under all load levels. We had obviously multiple processes running, benign processes running, and it was still able to detect at a pretty high accuracy. Some of the features Aiden mentioned, the LLC loads, the cache misses, and the DTLB. Those are the key features that we identified. And practical system level monitoring. With this accuracy, although there are some limitations, this could be applied system-wide to detect side channel attacks, hopefully with good accuracy. So some future work we've outlined, larger data set and any kind of classification context is always beneficial. Diverse and consistent background processes. So like we said, browsing, playing videos, anything that might naturally be done, and doing it consistent with the attacks to get that classification model. Different OSs and architectures. So ours was run on Linux. We didn't try Windows and we didn't try ARM architecture. So, those are different kernels, different computer instructions fundamentally. So be curious to see how it would work there. And because it's an ML application, you could try different models, k-nearest neighbors, support vector machines, neural networks. We used XGBoost, which is a tree-based classifier. And hyperparameter tuning is good for the model. We tried and played around with some different hyperparameters and didn't get drastically different results. So we think our hyperparameters were pretty solid and they're pretty basic, which in my experience, the simpler ones tend to do better. So this could be some future work. And these are our sources. So thank you for watching.